So we're going to start today studying discrete probability distribution. This is on chapter 6 in your book. It's on page 253. So we learned in previous chapters that there are two kinds of data. We have discrete data and we have continuous data. We also learned in a previous chapter about probability, and we learned about probability experiments. So today we're going to start section 6.1, talking about a little bit about random variables. So we have two definitions that we're going to write down in our notes. So the first definition is about a random variable. A random variable is a numerical outcome of a probability experiment. So we conduct a probability experiment, and any numerical outcome that we're going to obtain from that experiment is going to be known as a random variable. In other words, you don't know in advance what is going to be the value that your random variable is going to have. When you don't know that, you say that this is a random variable. If you define the values for your variable, then you don't have a random variable, you only have a variable. And also, depending on the kind of data that you are working on, so you know if you are working with labels, for example, you have categorical data. If you are working with numerical values, you have quantitative or numerical data. Now, numerical data is subdivided in discrete and continuous. So, and the same thing happens with random variables. We're going to have two kind of random variables. We're going to have discrete random variables, which are random variables whose possible values can be listed. And continuous random variables are random variables that can take on any value in an interval. So we need to remember a little bit about this kind of data that we learned in previous chapters. So we have here in our notes the definition of a random variable, the definition of discrete random variables, and continuous random variables. So if you remember our previous lectures, we said that when you can count, counting gives you discrete data. If you measure, if you perform measurements, then you get continuous data. So if you have a probability experiment, and you know a probability experiment is any activity that you are trying to do, an action or activity or process where the next outcome is not known. That is a probability experiment. So if the probability experiment is providing you with counts, then you're going to have now a discrete random variable. So it's random because it's coming from a probability experiment. It's discrete because you can list the possible values. So usually counts can be listed with whole numbers, 0, 1, 2, 3, 4, up to infinity. Or you can get also, as I mentioned before, measurements. Then you're going to have a continuous random variable. Okay, is random again because it's coming from a probability experiment. It's continuous because it's the result of measurements, and usually you cannot list all the possible measurements, so you talk about intervals. So any value in an interval, is going to be a continuous random value, so you're going to have a continuous random variable because of that. So we're going to solve some examples to understand this a little bit better. So we're going to start with example 6.1. So let me see, 6.1 is on page 254. So we're going to have example 6.1, and the example is the following. So it says that we have this question. So which of the following random variables are discrete and which are continuous? So the first one is the number that comes up on the roll of a die. Then the second case is going to be the height of a randomly chosen college student. The next thing is the number of siblings a randomly chosen person has. And finally, the amount of electricity used to light a randomly chosen classroom. You can see here in all these cases the word randomly here, randomly here, randomly here. So those words imply that this is the result of a probability experiment. And also when you roll a die, you know per nature of the die that is going to be random. The number that you're going to get is going to be a random number because you don't know in advance what the next number is going to be. So let's work on this problem. So example 6.1, I just wrote here part of the question. So we have here first when you are having or rolling a die, you know that you have numbers that you're going to obtain from here. So the probability experiment is just rolling a die. That's the probability experiment. Now, what are the possible values that you're going to get from here? That's going to be your sample space. Remember, the sample space is just 1, 2, 3, 4, 5, and 6. So you can see here that you can list the possible outcomes. So you don't know what is going to be the next number. So that's the reason this is going to be a random variable, A, and because you can list the possible outcomes, then this is a discrete random variable. Random because you don't know the next value that you're going to get when you roll the die. And you know that there are only these 6 possible outcomes. You don't have the possibility to get, for example, 2.5 or 4.3. So that is the reason this is discrete. So that's the solution for the first problem. Then we have the height of a randomly chosen college student. So what is the probability experiment? The probability experiment is you're gonna choose a college student at random, and then measure his or her height. So you're gonna measure. So first, this is gonna be a random variable because it comes from a probability experiment where you are just choosing students at random, and you're gonna measure his or her height. So that means that you're gonna obtain, you are dealing with a continuous random variable. So that's what we are dealing with in this case. Now, the number of siblings a randomly chosen person has. So what is the probability experiment? the probability experiment is that you are again choosing a person. You choose a person at random and then ask uh, how many siblings she or he has. So you're gonna have a count. So the person is gonna count her or his siblings. So because you are counting, so you know that the possible outcomes are 0, 1, 2. So you can list the number of siblings. The number of siblings are going to be 0, 1, 2, but you don't know the upper bound, but you know that you can have a list. So in this case, then, because this is a value, an outcome that is coming from a probability experiment, you have a random variable. Now, because you have a count, this is a discrete random variable. So that's the solution for this third problem. Now the last case, the amount of electricity used to light a randomly chosen classroom. So what is the probability experiment? The probability experiment is that you're gonna go out and you're gonna choose a classroom at random, and then you're gonna measure the electricity used to light the classroom. So you're going to measure that. So you're going to have a measurement. So you have measurements. And when you have measurements, you cannot list all the possible values that you can get. So this is going to be then, you're going to obtain a continuous random variable. A continuous random variable. So that's example 6.1. So now we're gonna learn about two more definitions, and then we're gonna solve another problem, and then I'm going to assign you some problems. So now the next definition is that we need to collect all this information. So when you are doing a probability experiment, you are getting outcomes. What you care about is what is the probability that you're gonna get one of those values later. So the way that we collect all that information, the way that we, in some sense, summarize the information about the outcomes and the probabilities of being uh, appearing or showing up is by using a probability distribution. So we're going to have now the definition of a probability distribution. So for a discrete random variable, uh, that probability distribution is going to specify the probability for each possible value of the random variable. And we also need to learn about those probability distributions that we call them discrete probability distributions. We're going to learn that if you have P of X denoting the probability that a random variable has the value X, then there are two conditions that the probability distribution should satisfy to be considered a probability distribution. So the first condition is the same that we mentioned before in the last chapter, is that any value of probability should be a value between 0 and 1. And the other condition is that the total sum of probabilities for that distribution, for that discrete probability distribution, should be equal to 1, or because sometimes we are dealing with rounding numbers, very close to 1. So now we're going to work another example to work on this. So just I'm going to show you part of the notes that I just wrote for you. So first, the definition of the probability distribution. So the way that we're going to see this probability distribution is in a form of a table. So we're going to have a table. We're going to have the variable on the first column, and we're going to have the probability of every value on the second column. So here you're going to have a list of values. Usually, most of the time are going to be integers. So this is a numerical variable. So be careful, because sometimes you're going to have labels to indicate some outcomes of an experiment. For example, remember the credit card problem, and you might have the probability of getting a customer using a MasterCard or using a Visa or Discover. But in that case, when you have labels, then labels are not a numerical variable. Labels are a categorical variable. So in that case, that cannot be considered a discrete probability distribution. That cannot be considered a probability distribution either. So we need to have a numerical variable, and this is going to be a random variable. So you're going to have values like 0, 1, 2, 3. So most of the time, all the time should be numerical values. Then you're going to have a value here between 0 and 1. Remember, between 0 and 1. So any value here should be 0, between 0 and 1. So we're going to have value here, another value here, between 0 and 1, between 0 and 1. No negative values, so be careful. And the sum of these values in the second column should be always close. I'm going to use this notation to indicate that it's going to be very close to 1. So the table looks like a frequency distribution, like a relative frequency distribution. But to be considered a probability distribution, the first column should be a numerical variable. Numerical values should go on the first column. And also numerical values on the second column, but those values are going to be restricted to a domain between 0 and 1, all of them. If you have only one value that is a negative value or greater than 1, then immediately the entire table is not going to be considered a probability distribution. So you have here those conditions that I just mentioned, and we're going to work now an example. So we're going to work on example 6.3 on page example 6.3 on page 255. So let me show you that example. So it's here. It's at the bottom of the page. So what we have here is the following problem. So we have here different tables, and the question is we're going to need to identify probability distribution. So you have 4 tables, A, B, C, and D, and we want to know whether those tables are representing probability distribution. So the problem then is that we're going to identify the probability distribution. So I'm going to write here the solution. So the question is, which of the following tables represent probability distributions? So that's the question. So we're going to start with the first one. So the first one. So you have numerical values. Perfect. 1, 2, 3, 4. And you have numerical values in the second column. But yeah, you get a negative value here. So you have a value. So for x equals 3, px is negative 30. So this is not acceptable. Not acceptable. So for that reason, this is not a probability distribution. So it looks like one, but it's not. Now the second one. So now we have in the second case we have now this table here, numerical values on the first column. Perfect. It doesn't matter whether some values are negative and other are positive. It doesn't matter that as long as they are numerical values. Now the second column, we're going to check that they are values between 0 and 1. So you have values between 0 and 1 in the first case. The second case satisfies the condition. The third and the fourth and the fifth case too. So the only thing that we need to check is that the sum of these 5 values is pretty close to 1. So let's do that. So we can use our calculator, or you can use your R console. So the only thing that I'm going to do is I'm going to add up the probabilities. So I have 0.17, 0.25, then 0.31, then I have 0.22, and finally 0.05. So we get 1. Perfect. So it seems that there are no other situations preventing us to say that this is a probability distribution. So for B, so every value satisfy the condition. So every P of x was between 0 and 1, and also the sum of the probabilities was exactly 1. So yes, this is a probability distribution. So I'm taking time to explain this very clearly, because everything is going to depend on you being able to identify probability distributions, because later we're going to use these values to make decisions. So the third case. Now the third case, we have another table. So we have values for x that are numerical, so that's perfect. So then we have one value, the first one. The first value is greater than 1. So for x equals 1, we have that p of x is greater than 1. So because of that, yeah, no, this is not a probability distribution. So that's the solution for the third table. Now the fourth table. So the fourth table, we have now again numerical values for x. We have probability values going from that are between 0 and 1 in those 4 cases. So the only thing that we need to check is, so for every x, we have the probability between 0 and 1. So that's perfect. But we need to check now the sum. So we need to check the sum of those 4 values. So let's do that. So I'm going to use R again to verify the sum of those probabilities. And that's what we're going to get. The first is 0.10. And then we have 0.17. Then 0.75. And finally 0.24. So we are getting the sum of the probabilities equals 126. So that's something that we don't accept. So in this case, because the sum is greater than 1, then the answer is no. It's unacceptable. So this is not a probability distribution. So now I'm going to give you a very short assignment. It's gonna take you a couple of minutes, and then we're gonna continue with our work. So I'm going to give you an extra table. I'm going to give you our table E. Is gonna be the following, so we don't need this anymore. So I'm going to give you one more table with a frequency distribution or something that look like that, and you're gonna tell me. So whether that is a frequency probability distribution or not. So I have A, B, C, D. I have 0.10, 0.50, 0.30, and 0.10. And you're going to answer the question, is this a probability distribution? So take a couple of minutes to analyze this table and answer that question. So the answer to that question is no, right? Because you don't have a numerical variable, you don't have a random variable x, because you have labels. You have A, B, C, D. They are labels, they are not numerical values. And even though you have values for the probability between 0 and 1 in each case, and you add up all those values and you get 1, that is not a probability distribution. So we need numerical values for x. So now we're going to solve another example. We're going to start using the probability distribution to answer questions about probability of certain events. So we're going to have single events and we're going to have compound events, but now we're going to use the information that a probability distribution is going to provide. So we're going to solve now example 6.4. So example 6.4 is on page 256, and we're going to start reading, we're going to continue reading very, very carefully every problem. So this example 6.4 is this one here. So we have 4 patients that who have made appointments to have their blood pressure checked at a clinic, and we're gonna let capital X be the number of them who have high blood pressure. So based on data from the National Health and Examination Survey, the probability distribution of capital X is, and then we have that table. We have lowercase x, 0, 1, 2, 3, 4, and the probability of every value of x is given there. So 0.23, 0.41, 0.27, 0.08, and 0.01. You can check that the sum of those probability values is 1, and you can also see that every probability value is between 0 and 1. So now we have questions about events, and we need to compute the probability for every event. The first case is just the probability that x is going to be equal to 1 exactly. The second case is that what is the probability that x is equal to 2 or equal to 3. Then what is the probability that x is going to be more than 1, greater than 1. And finally, what is the probability that x is at least 1. So in other words, that x is greater than or equal to 1. So we're going to copy this in our notes, and we're going to start working on this problem now. So we have here the problem and the table. I just copy the table in a vertical format. So they are talking about capital X. So if you read the previous definitions in our book, they say that random variables are denoted with capital letters. So this is a capital X. So this is a random variable. The random variable in this case is the number of patients out of 4, because there are only 4 patients, who have high blood pressure. High blood pressure. Capital X, you can just write the numbers. 1, no, we start with 0. 0, 1, 2, 3, and 4. So we have 5 values. So now every single value is going to be denoted with the lowercase x. So capital X is all the x's, and lowercase x is just a single one. So the first problem then is we're going to find the probability of x equals 1. So you can write it in this way. You can also write it as in this other way, x equals 1. The meaning is the same. So how do you solve this problem? You just need to check the table. So you look at the table, look for x equals 1, and read the corresponding probability in the second column. So the answer is just 0.41. So that's the first one. So just read the table. That is the only thing that you need to do. Now, the second case. So it says the probability that 2 or 3, that x equals 2 or 3. So this is going to be equivalent to saying that you have the probability of x equals 2, and or means that you're going to use the addition rule for probabilities, and the probability of x equals 3. You don't need to subtract the overlapping or the intersection, because it's either 2 or 3, but it cannot be x equal to 2 and 3 at the same time. So, and then you just read it from the table. For x equals 2, you find 0.27. For x equals 3, you read 0.08. So we need to add these two values. So, and we're going to get 0.35. So now the third case. In the third case, we're going to find the probability of x being more than 1. So this is the same thing as saying the probability of x greater than 1. This is a compound event. Again, we're going to use the addition rule. So this is equivalent to getting the probability of x equals 2, because 2 is greater than 1, plus the probability of x equals 3, because 3 is greater than 1, plus the probability of x equals 4, because 4 is greater than 1, and that's it, because there are no more values in this table. So we're going to get just the corresponding values from the table. So 0.27 plus 0.08 plus 0.01. So you have just this. This is the extra value that we're going to use with respect to the previous problem. So the answer is just 0.36. Finally, we have part D. We want now the probability of at least 1. So read carefully these expressions. more than 1 and their equivalents, equivalent expressions in algebraic notation. So more than 1 is just greater than 1. At least 1 means that it's going to be greater than or equal to 1. So that's the difference between these two cases. It's important to read carefully. At least 1 means 1 or more, and more than 1 means only greater than 1. So in this case, is the probability that x equals 1 plus the probability that the x equals 2 plus the probability that x equals 3 plus the probability that x equals 4. So we're going to need to add 4 values. So 0.41 plus 0.27 plus 0.08 plus 0.01, or you can use the complement rule, the rule of complements. So when you have all these values that you're going to add up, is the same as subtracting the only value that is remaining here out of the game from 1. So that's another way to get the answer. Is going to be equal to 1 minus the probability of x equals 0, because that's the only value that doesn't satisfy the condition x greater than or equal to 1. So 0. So this is equivalent to 1 minus 0.23. If you do these computations, you're going to get 0.77. So, and you get from here also 0.77. So those are the problems that used a probability distribution to find the probabilities of certain events, single events and compound events. So now you're going to work a lot of problems. In this class work requires you to work a lot of problems, very simple problems. So it looks like it's a lot of work, but it's not. It's just very simple problems, just additions, subtractions, if you use the complements rule. So we're going to work on section 6.1 exercise set on page 265. So first you're going to determine whether you have a discrete or continuous random variables, and then you're going to also answer questions to know whether you have a probability distribution. So you're going to work in the first case, problem 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So in these cases, you're going to determine whether you have a discrete or a continuous random variable. Then in the next subset, so we're going to continue with problem 27, 28, 29, 30, 31, and 32, and then you're going to determine whether you have a probability distribution or not. So I'm going to show you the corresponding problems for you to work. So first 17 through 26. 17 to 26 is just a little piece on page 265. So let me see, let me show you. You have here all the problems. 17 through 26. Okay, so you just determine whether you have a discrete random variable or a continuous random variable. So you can take a screenshot now and read every problem carefully. You're not going to take a lot of time to do it. So now we're going to work problems. I'm going to show you problems 27 through 32. So first 27 through 29, 3 tables, and you're going to determine whether those are probability distributions, those three. Take a screenshot, copy the values, pause the video, and then the other three are here. So now we're going to continue with more work that we're going to do with the discrete probability distributions. The first thing is that we're going to construct some probability histograms. So we're going to use table 6.3 to get the histogram like the one that you see in figure 6.1. So table 6.3 is just the probability distribution for the number of boys in a family of 5 children. Using the assumption that boys and girls are equally likely and that births are independent events. So we have just a probability distribution here. So you have a numerical values for the random variable x. You have values for probability that satisfy the conditions that they should be between 0 and 1, and also the sum of these 6 values is going to be 1. So I'm going to show you how to build a probability histogram like this. It's slightly different than the way that we used to create histograms in the previous sections. So the first thing is that we're going to enter the information from that table. So we have x can be entered as a collection of these 6 values, or we can use also this notation that is very helpful when you are dealing with discrete probability distribution with discrete random variables. So remember, this is the lower limit and this is the upper limit of your list. This is useful when you have consecutive numbers only. If you don't have consecutive numbers, you need to enumerate the numbers by using this form. But if you have consecutive numbers and you know the minimum value and the maximum value, then this is a better way to do it. Then we have to enter our variable for the probability value. So I'm just writing px and writing the values from the table. The first value is 0.03125 and so on. So we have 6 values. So one value per one value of x, one value of probability for per value of x. Then we're going to use this command. So we're going to use the bar plot command instead of the hist command, even though we're going to create a histogram. The only way that we're going to make this plot to look like a histogram is by setting the space between bars equal to 0. So if you set the space between bars equal to 0, then the bar plot that you're going to get is going to look like a histogram. So I'm going to enter this information into R, and then we're going to see the corresponding histogram. So I have here those values. So I'm going to enter bar plot px names r equals x, and finally space equals to 0. So if we do that, we get a histogram like the one that you have in your book. So that's the histogram. Now we're gonna start getting some. This is the graphical summary of our probability distribution. Now we're gonna get this numerical summary. If you remember, we have measures of center, measures of spread. Those are gonna be the numerical values that we're gonna compute to get the numerical summary for any probability distribution. So let's go back to our notes, and now once you finish this, I'm going to start now talking about the mean of a random variable. So you have a formula on page 259. So the mean of a discrete random variable, we multiply each possible value by its probability, and then we add the products. So another name for the mean of a random variable is the expected value. And when you use the expected value terminology, then you use a capital E parenthesis X to indicate expected value of X. So when you read expected value, they are talking about the mean, so they are equivalent. So we have then the formula. We can use R to do our computation, and we can do it by hand. So we're going to go now example 6.6. Example 6.6, we're going to have a probability distribution. Now we're going to learn how to compute the mean and later the standard deviation of a probability distribution. And you're going to see that the formulas that we're going to use are very similar to the ones that we used when we computed the mean and the standard deviation from a frequency distribution, because you can see that the probability distribution looks like a frequency distribution, a relative frequency distribution. So we have this problem. A computer monitor is composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. So let capital X represent the number of defective pixels on a randomly chosen monitor. Then we have the probability distribution of capital X as follows. So we have values for lowercase x, single values of X, and their corresponding probabilities. So we're going to find the mean number of defective pixels. So that's the problem that we're going to solve. So we have here the table that we're going to use. That's the table. So the problem is that we're going to find the mean. Find the mean number of defective pixels. So we're going to do this problem by hand. It's a very simple problem. So we need to add an extra column where we're going to multiply X and the corresponding probability. So in the first case, you're going to multiply 0 and 0.2. So that is going to be 0 times 0.2 is just 0. Then we're going to multiply 1 times 0.5. This is going to be 0.5. Then we have 2 times 0.2. So that is going to be 0.40. And finally, 3 times 0.1. So this is going to be 0.30. Then we're going to get the sum. The sum of these values are going to be just, you can use a calculator, or you can do it by hand too. So the sum is going to be 1.20. So the mean is going to be 1.20. So you can write this as mu of capital X equals 1.20. So now let's solve one more problem. So we're going to solve example 6.7. So example 6.7 is on page 260. So let me show you the problem. So the problem is here. We're going to determine the mean of a discrete random variable again. So let capital X be the number of boys in a family of 5 children. The probability distribution of capital X is given in table 6.4. So we're going to find the mean number of boys and interpret the result. So table 6.4 is here. So if you remember, this table is the one that we used to create a histogram. So now we're going to use the data that we already have in R. So let's see. So in this problem, the solution is very simple because we already have in R this information. So let's see, we're gonna find the mean. So in this problem, we're gonna find the mean of capital X, where capital X is now the number of boys in a family of 5 children. So let's see, we're going to use just the sum of the products because we already have this information in our computer. So you can see that information here in R. So that's the histogram for that probability distribution. We have here the values. So that table shows information for 0 through 5 and the corresponding probabilities. So now we're going to just get the sum of x times the probability, px. So we get 2.5. So that's the mean. So we're going to write 2.5 for this problem. So the mean, this sum is 2.5. So if you want to do it by hand, just check the book on page 261 and you're going to see a table like this one where you're going to see an extra column with products. You can see it here. So this is the value for x that we enter, the value for the probability, and now they computed the product of these two values, these two columns, and then they add up all those values and they got 2.5, which is the value that we just got. So that's the example 6.7. Now we're gonna work finding the standard deviation. So this time we're gonna work on page 261. So at the bottom of the same page we have the formulas for the standard deviation. So these two formulas are equivalent, but the second one is most useful when you're using calculator or so software. So that's the one that we're going to use. And remember, the standard deviation is just the square root of the variance. So this formula is for the variance, and this formula is for the standard deviation. You can see that you're going to multiply now, instead of multiplying x and p of x, now you're going to multiply x squared and p of x. You're going to add all those values, but you need to subtract the square of the mean that you computed for from a previous step to get the variance. So we're going to solve an example to apply this formula. So we're going to solve an example. I'm just going to show you the formula that we're going to use is here. The variance and the standard deviation of the discrete random variable. So this is the formula for the variance. I'm going to write here variance. And then you get the square root, and that is going to be the standard deviation. The standard deviation, remember, is going to be just the square root of the variance, the value that you obtain, that is going to be. So let's work now on example 6.8. Example 6.8 is here. So that example is about the pixels, the defective pixels in a computer monitor. So remember, we have this probability distribution with values x0, 1, 2, 3, and p of x being the values for the corresponding probability. So now we're gonna do it by using R. If you want to check the solution that your book provides, it's a lot of computations. So that's one way to do the problem. But in both cases, you're gonna need to compute first the mean. So let's do it by using R. So what we're gonna do now is we're gonna use a different variable. So you can have x and p of x, so you can have y and p of y. It's exactly the same thing, because I don't want you to confuse you with the previous problem that we just entered. So I'm going to enter y equals and the four values that are in that probability distribution and the also corresponding 4 values of probability, and then we're going to find the mean first by applying now the formula y times p of y, and when we find that value we're going to put it here, and then we're going to have now to compute the sum of the squares of y and the corresponding probabilities. Remember, these formulas are, you can be written also when you have x and p of x. So I'm going to rewrite those formulas for you to have it. So remember, when you have a probability distribution, the mean is going to be obtained by adding the products of x and p of x, and the standard, the variance is going to be obtained by adding, we're going to add right here, we're going to add the sum of x square times p of x, and we're going to subtract the mean that we just found before, square. So that's the formula in terms of x, and that's the formula in terms of y. So let me just enter this information into R to finish this program and to assign you some work to do. So let's see, let's go and check R. So we're going to start with y now. Y is a collection of values 0, 1, 2, and 3, or you can use 0 colon 3. Then p of y is going to be the collection of 0 0.2, 0 0.5, 0 0.2 again, and 0 0.1. Then we're going to get the mean just by writing the sum of y times p of y. So that value is 1.2. We found that value before. So now we're going to enter that value in our formula. So we're going to write now the formula for the standard deviation. It's again a sum, but now we're going to square y before multiplying that value and the corresponding probability. And then we're going to subtract that value that we just found, and we're going to square it. So that is going to be the variance for that problem. So, and we're going to take the square root of that value to get the standard deviation. So I'm going to write those values. So first we got 1.2 for the mean, then we got 0.76 for the variance, and then the square root of 0.76 was 0.87. So I'm just going to show you the values I'm just collected from the display. So this is the mean, this is the variance, and this is the standard deviation. So when we apply this formula, we got 1.2, then we put 1.2 here, then we do this operation, and we got 0.76, then we take the square root, and we got this. So this is the standard deviation of the values. So you have the formula if you want to use x's instead of y's. So the answer is going to be the same. I'm just going to assign you a couple of problems to solve. So, and that is going to be all for this section. So we're going to go again to section 6.1, exercise set on page 266, and you're going to solve two problems, 46 and 47. So let me show you the corresponding, let me see, 46 and 47. Perfect, you have two problems to work on. So the problems are here. So let me show you the first one. 46 is about texting. So you have your frequency distribution, here with values from 0 through 5, the corresponding probabilities, and you're going to find first probability of some events, for example, when x equals 2 or when x is greater than 1. And then part E, you're going to compute the mean. Part F, you're going to compute the standard deviation, which is what we did in the last two examples. Then you're going to solve problem 47. This is a similar problem. So you're going to have to work on this. You have a frequency distribution. So remember, you need to convert these frequencies into relative frequencies. And in that way, they're going to be used as probability values. So that's the first thing. Part A is just getting the probability distribution, is just getting the corresponding probabilities just by dividing the frequency over the total frequency. Then you're gonna solve some problems about computing probabilities. That's part B and C. And finally, part D is computing again the mean and the standard deviation.